Hi everyone. In this episode of the Bitcoin from Scratch series, we're going to be finishing up our elliptic curve code such that we can actually use it for elliptic curve cryptography and Bitcoin key generation. So in the last episode, we left off describing how our current point addition and point class assumes that these are all floating point numbers. We're just usually using regular division in some of these computations. But to actually use it for cryptography, in Bitcoin specifically, we need to compute on a field of integers, or like the set of numbers that we'll be considering is integers mod some prime. So we're going to actually define this prime, which you can just find online. This is a publicly known value for the Bitcoin curve, and that is represented in hexadecimal here. I already have it copied, so we'll just slot that in. And we're going to use this in our redefinition of this division, or what's called modular inverse, considering this prime number. So that's going to be the first thing we do in this part. Let's make a new file called modular inverse. And we are going to define a function. We're just going to call it inv, and it's going to take in a and our prime number. So for those not familiar, I would recommend you brush up on modular arithmetic if you haven't heard of it or used it before. But basically what we want to find here is a times x such that this equals 1 mod r prime. And what this means, let's just go through a simple example of this. If we have a equals 3 and p equals 7, 7 being a prime number, then we want to compute ax such that it's 1 greater than some multiple of 7, or it's equal to 1 mod 7. So what are those numbers? 7 plus 1 is 8, 14 plus 1, 15, 7 times 3 plus 1, 22, and so on. What x satisfies this equation? We can see that there is no x to get, 3 times x equals 8, but there is such that 3 times x equals 15. So obviously that would be 3 times 5. So we have 3 times 5 equals 15. Mod 7 is equal to 1 mod 7. So this implies that the inverse of 3, 7 equals 5. Okay, so this is the basic idea of what this function will return. In this case, it would return 5, but we want to do this for any a and p. So I'll just comment this out, and what we're going to use to define this function is called the extended Euclidean algorithm. So I have the Wikipedia page open for this, and this is kind of the key equation that we will derive this from. So the extended Euclidean algorithm we can use to get x and y such that ax plus by equals the GCD of a and b. So we have, let's keep note of that, ax plus by is equal to the GCD of a and b. And actually we're going to use p in this case. This can be used for a more general case even than we'll use it for, but we will have, we'll always have a prime number here, so let's call that p. So why this works, or why this is useful to us, is that the greatest common divisor, which is what this GCD stands for, of any number and of some prime is always going to be 1. So that's based on the definition of a prime number. A prime number has no divisors other than 1 in itself. So the greatest common divisor obviously is going to be 1 in that case if there are no other divisors, kind of by definition of a prime number. So let's just swap this out, and let's just say 1 mod p. Okay, but if you think about what this actually gives us, we already kind of talked about how any multiple of that prime number is now going to be 0. So if this were, in our mod 7 example, if this were 7, 14, 21, 28, etc., p times y is always going to be 0. So we can actually simplify this to be ax equals 1 mod p. And not surprisingly, this is actually a very useful thing to know. If you recall back to our definition of what is a modular inverse, this is actually exactly what we want. So we're going to find x using this extended Euclidean algorithm. Okay, so I'm going to just copy this pseudocode. There are many more details, obviously, that I'm just glossing over here. If you want to read through this Wikipedia page, there's also plenty of resources. You can find videos and such to describe this algorithm further. We're going to quickly translate this pseudocode now just to Python code, but I will speed this up. Okay, so we have our pseudocode converted to Python, and you'll see we end up with a few variables here that we can use to find this x. So it tells us that the Bezout coefficients, which if you go back to the Wikipedia page, you'll see that those are x and y, such that it satisfies this equation we discussed. So these Bezout coefficients are old s and old t once this algorithm is complete. So as we talked through in our example, we actually are only interested in this x, as this x is the answer to the problem we're interested in. So we're going to return this old s, and we actually don't even need this old t. So I'm just going to delete that entirely. Delete this, we don't need. And we can return, once this algorithm is complete, old s. But in the case that old s is greater than the prime number, we actually just want to return the simplified version of it, or what's called the residue, mod that prime number. So we can just mod our results by p in that case. Okay, so this is our inverse function. Again, this very simple algorithm here. We're going to use this in place of all of our previous divisions, and I'm just going to delete all of the comments we had there. So now, how do we use this in our elliptic curve point addition? We can first import it. And we're going to just use it in place of all divisions. So instead of dividing by this term here, we are going to multiply by the modular inverse, mod p. So and our p will come from the curve here, which is an instantiation in the point object. So we can do self.curve.p. And we can do the same for any other instances of division that we have. Okay, next we want to actually just mod any other calculations any other results through this point addition function here. We want to just mod these by p as well. So, by the way, this is the way that you mod in Python, so we'll wrap this in parentheses and mod self.curve.p. Oops. And there's actually just one other minor update we have to make here, which is that when we check for inverses, so if the 2 points that we're adding are inverses of each other, we can no longer check if self.y is equal to the negative version of other.y. As we just said, that this other.y value will always be the residue because we're modding it by p here. So the residue meaning it'll be a number between 0 and the prime instead of a negative number like below 0. So the way we can do this is, like for example, if we were looking for 3 mod 7, the negative version of that is negative 3 mod 7, which the residue of is 4 mod 7. So you can actually just subtract off the prime, which is 7 in that example, and then flip the sign of it. So we're just going to put parentheses here and minus self.curve.p. Okay, so we're going to take, again, the negative version of other.y minus the prime. So next, let's just verify that our inverse code is actually working. Do if name let's just print the inverse of 3 mod 5 and let's do 5 mod 11. So in the first case here, we should expect 3 times 2 equals 6, which is 1 more than 5, giving us the inverse. And 5 times 9 is 45, which is 1 more than 44, or 11 times 4. So we should expect 2 and 9. And I need another underscore here. Okay. And that is in fact what we get. So I think we can be confident that our inverse code is working correctly here. Next, we're going to jump into point multiplication. So we've now defined our add method here. We actually are going to want to be able to multiply by a scalar. And this is the really critical part of Bitcoin key generation. Really how you generate a public key from a private key is you multiply the Bitcoin generator point, which we'll talk about what that is, by the private key, or some scalar, some integer. So we're going to go ahead and talk about how we can actually multiply a point by a scalar. So we'll go ahead and create a file called double and add. And this will just be a file for scratch work. We will eventually implement this actually in the point class itself. But what do we really mean by point multiplication here? So we know we don't have any sort of multiplication operator defined on this elliptic curve point class, but we do have a conception of what multiplication is in integers or in real numbers, for example. So what do we really mean by 3 times n, we'll say? So for any n, integer n, what we really mean by this is we want to add 3 to itself n times. Right? So 3 plus 3 plus itself, and so on until this happens, a total of n times. Okay, so if we were using small numbers n, we could just write up a quick function to just do this, add the input to itself n number of times and call that multiplication. However, in our code, we're going to be adding this to extremely large numbers. So if you recall, the prime number we're going to be working with, that will basically be the upper bound of our private key integer. This is on the order of like 10 to the 70, 10 to the 71, I believe, which is an astronomically large number, on the order of like the number of atoms in the universe large. So obviously we're not going to be doing any sort of iterating to add this number to itself that many times. So a more efficient algorithm that we can implement is called the double and add algorithm. So let's just create a quick function here called multiply, and let's implement it for integers first, and then translate it to elliptic curve points after that. That sort of makes it easier to grasp. So I'm just going to comment these out, and let's just say we're going to multiply. We can actually just do self and other. I think that is easy enough, because this is how we'll implement it within the elliptic curve class. So we're going to start with this, we're going to call this track. So this is just going to be a list, and we're going to initialize it with the first element being a tuple with 1 and self. Okay, so self being the number we're adding over and over again, and this will be our sort of tracker. So the 0th position will be our tracker, and the 1 position will be our result. We're going to continue doubling both of these. So we're going to do while loop here, and we're going to check if our tracker is greater than the number of times that we want to add this number to itself. So track, we can index the last element of the list, which currently is just one element, and we can check, we can grab the tracker, we can double the tracker by adding it to itself. Remember, we can't do like times 2 here because we don't have, with the points, we don't have any sort of multiplication defined yet. So we can do, the tracker plus itself, and let's check if this is less than our other point. Oops. And remember, this other is a scalar, so we can always, we always have some concept of less than or greater than with our integers, obviously. So if it is less than other, then we are just going to append to the track list, and we're going to we're going to append another tuple with the updated values. So we're keeping track of all the previous values, but we're going to update the list here. And we're going to add the tracker to itself, and then we're going to add the result to itself. So the firstth element of the tuple. Okay, we're going to continue doing this until the next double would exceed our expected result. So let's just print this to kind of get an idea of what's happening here. So we want our tracker, and then we'll do our result. And our tracker is as we said, the first element of the tuple, and the result is the second. So let's just print what's going on here. I'm actually going to add one more print before the loop starts as well. We need to actually call the multiply function, obviously. So let's do this with a reasonable number. Let's just do maybe 3 times 15, and we can get a sense of what's going on here. Okay, I meant to do tracker. But you can see here that our tracker is getting doubled every time, obviously, as is our result. So we start with 3, and we go 3 plus 3 is 6, 6 plus 6 is 12, 12 plus 12 is 24. The purpose of this tracker is to say, okay, if we double this, we have now doubled more than our other here, or the number of times that we are supposed to add this number to itself. We've actually done more additions if we double again. So we have to stop there, right? We can't do 8 plus 8 is 16, because that is greater than 15, which is our other here. Okay, so what we do then is we actually are going to iterate backwards through this list so that we can keep adding smaller and smaller values until we reach that expected result. So what we're going to do is, with a for loop, we're going to unpack these tuples now, and let's just call it track and result. Let's go backwards through the list to start with the larger values, and we will just do track. I think can't reuse that name, so let's just do tracker and result. So similarly, we're going to check if we were to add this smaller value now to the ongoing result, or the last element of the list, would we exceed that threshold that we're looking for? So let's check if we add to our last tracker plus this new element that we're testing out, that we're iterating through. If this is less than or equal to our other, or the point we're trying to, the number of additions that we're doing total, then we can go ahead and add it. So let's track.append, and we can actually just copy this whole addition here. So this will be the first element of the tuple, but then we also have to update our result as well. So we can do our current latest result, or the last result in the list, plus the result that we are iterating through. Okay, and this is maybe a little confusing just looking at the code, but let's again, we can print what's going on here and hopefully get a better grasp on it. So again, sticking with our 3 times 15 example, and you'll see we do end up with 45 as expected, 3 times 15. But you'll see how we got there is the more interesting part. So with our tracker, we did 1 plus 1 is 2, and so on until we got into 8 plus 8. We realized 8 plus 8 is greater than the number of additions we're trying to do, 15. So let's start going backwards through the tracker list. And we realize, okay, we can do 8 plus 4, because that will not exceed 15. And we can also do 8 plus 2. We can also do 8 plus 1. So we go 8, 12, 14, 15, and we realize, okay, now we have completed our addition, our set of additions here. And we end up with our correct result. So we did this with 7 iterations, you'll see. If we would have done it the way we first described it, would have been 15 iterations. So we saved about half of the number of total iterations there, or just under half. But this savings actually scales exponentially. So if we were to multiply by 15, we don't get much savings. It would be pretty fast anyway to iterate 15 times. But what if we were to do, 150 billion iterations, which seems like a big number, but this is actually a tiny number compared to what this would be if we were really generating private keys. Okay, so if we were generating private keys, we would select a random number between 1 and 10 to the 70 approximately. So this is a tiny, tiny private key, and in this case, you would be iterating for probably hours or days if you were to do it in this straight additions, if you actually added 150 billion times. Okay, but we can try it out, and let's see. You get a much faster algorithm than if you were to iterate straight through it. And you'll see we can actually check where did we stop doubling here. So we doubled. So we doubled until this point, and this is where you really get that cost savings or the time savings, because we get to take advantage of exponential growth here. So we double until we reach this threshold. If we were to double this result again, we would exceed our 150 billion times 3. So then we start adding in reverse, and it doesn't take too long until we achieve our result of 450 billion here. So this is the double and add algorithm. It might look confusing at first glance here with all of the looping going on here, but it's a very simple algorithm and not super critical to understand for the grand scheme of things, but I think important to show how we're actually doing this in terms of the elliptic curve. So we can actually just copy this straight away and paste it into, let's remove our print statements. Can remove that. And we can just copy this and paste it straight into our class here. So this is our point class where we have our add method. We're going to use that add method, and here this will take in self, which should be a point, an instance of the class, and it will take in as other a scalar. So we just need a couple last changes to fully test this out and validate that it's all working. First, we're going to change this multiply to be the dunder-mul method so that we can call it with the operator rather than typing out multiply in the same way that we do it with add. Next, we are going to introduce a point called the Bitcoin generator. So we'll cover this in more detail in the next video, but this is basically a point that is publicly known to be on the curve, and it has it's used for key generation. So the reason we need this Bitcoin generator point is because we can no longer do this square root. We can't do this for all examples, basically. We need to find examples where we're dealing with only integers now that we're using modular arithmetic. So I'm going to delete these. Let's just define the Bitcoin generator here. So we should have Bitcoin G, and we'll check that this is on curve. One last thing we need to do before we actually do a multiplication example is we need to go back to our isOnCurve function here, and we need to mod by that prime number. So now that we're dealing with large numbers, it's very likely that squaring it is going to push it above that upper bound of our prime modulus. So as we always do, we need to get that modulus. So mod by self.curve.p. And same here with our right-hand side. Okay, so let's take a look at this. Let's do Bitcoin G times 3. Actually, let's assign this instead of print. Let's assign this to a point called G3, and then we can G3 is on curve. Okay, great. So we have our Bitcoin generator. We have a scalar multiplication of the Bitcoin generator, both on the curve. And this in turn validates all the code we've written so far, as the multiplication also calls the add method, or it's basically built upon the add method. And just one last sort of example one last edge case I want to cover is where we're returning the identity point here. So we've covered what happens when points are inverses and we have to return the identity element. What we have not covered is what if self or other here is the identity element. So in the same way when we do like 2 plus 0 equals 2 in integer addition, we want to do, if a point plus our identity is computed, then we want to return that point. So anything plus the identity is itself. That's how it's defined. So if self.x equals none, we'll return other. And if other.x equals none, we will return self. Okay, so that'll cover our identity edge case when we get into doing more of these multiplications. So as I mentioned, in the next video, we'll be talking more about this Bitcoin generator point and how that relates to Bitcoin key generation. So thanks for watching, and I'll see you there.